Well, once more into the breach for the final time. Anyhow, what I'm going to do today is spend the first 20 minutes going over the material that I expect you to know well for the final. So, the first bit of information I want to bring your attention to is to remind you of all the help that's available for the next week. Number one, you will have recitation tomorrow. You'll be handing in graded homework number 12. And you'll also have the office hours of your TA. Tomorrow at 7:15, in the dark of a cold morning, I shall be available at 7:15 in Math-501. That's in the Math building, Math-501. I'll also be available on Thursday at 8 o'clock in Math-501. Then, Brittany is available at 9 o'clock in Math East 241 on Thursday. On Friday, Bowen and Celine, respectively, are available at 10 a.m. and 1 p.m., again in Math East 241. Then, on the following Monday, between 10 and noon, we have Caitlin and yourself, right, at, again, Math East 241. Then on Tuesday, the 17th, the day before the final, between 10 and noon, I will be available in Math 501. Okay? The best material for you to test yourself against is the trial final and the other trial exams that I posted online and that was handed out several weeks ago. Let me go over, though, the material that's the most important for you. The most important material is essentially the course split into 3 parts. In part 1, roughly the first third, we talked about first order ODEs of the form dy by dx is some given function of x and y. There were millions of methods. If you look in the books, there are lots of methods, but we only stressed 4. Method 1 was if it's separable. In other words, if this is just a product of a function of x times a function of y, then you can essentially separate the y's from the x's and then integrate. So you separate and integrate. Method 2 was also separable, but it was autonomous. In other words, the independent variable x didn't appear in the equation. In that case, you could solve it, of course, using the separable method, but you can see exactly what the solution does by simply drawing the graph of f of y, if x isn't present. And from that graph, you can argue what the equilibrium fixed points are, and you can also tell exactly if you start in any place where you will end up going. Then, of course, we had linear equations. If it's linear, it doesn't have to have constant coefficients or anything like that. We use the idea of an integrating factor and then solve. And then in all cases, although we won't be using this on the final, the JODE, using the software to actually check what the solution looks like. Equally important to methods, in fact, in a sense, more important, are the applications. The first application was the mixing problem, pouring brine into a tank and having stuff coming in and stuff fluxing out, and your job is to find what the final or what the state of the system is at any time, and in particular, often you're most interested in what it looks like for long times. Cooling problems. Cooling of dead bodies or cooling of cakes. Okay, it doesn't matter. You have Newton's law of cooling, which says that the rate of change of temperature is proportional to the difference between the temperature of the body and the temperature of the ambient, the surroundings. In other words, the difference between your temperature and the outside air temperature tells me how much heat is fluxing out of your body and roughly the rate at which your temperature is falling. Okay? But the constant of proportionality, of course, is negative because heat flows from the higher temperatures to lower temperatures, at least in most universes. The next problem, radioactive decay. Essentially, the quantity of radioactivity of any isotope, of some whatever, metal, you have the equation that the quantity, the rate of change of quantity with time, is proportional to the quantity remaining. So dq by dt is minus kq, where k is a given constant. Then populations. Populations grow, usually grow anyway. The rabbits, you have, if x is, say, the population, say, measured in thousands or millions of rabbits, dx by dt is kx. That's the simplest Malthusian law. In other words, the rate of growth is proportional to the number present. Makes a lot of sense. But then maybe if you have a limited environment, a limited set of resources, that may be modified by kx minus something x squared, where the which says that effectively that, you know, there's, once the rabbit population grows to a certain level, then the resources more or less balance at that point, and you can't produce any more rabbits. And then you can add hunting to it. We've had those models. Falling bodies, essentially under the gravity, and two kinds of friction. The friction which is proportional to the velocity of the motion, that's slow flow. Okay, like for instance, your blood in your capillaries flows very slowly. Okay, but if you jump out of an aeroplane with a parachute, then the friction law is proportional to your velocity squared. So both cases, and this is very important to know all about electric circuits because they're so straightforward. The rules are very simple. The rules are given by Kirchhoff, 1 and 2, which says the current at any node, the amount of current in is equal to the current out, and the sum of the voltage drops around every closed circuit is 0. And applying those two laws, you can find the differential equations which describe the behavior of circuits. Then we go on to the second part of the course. We talked about second order systems. In fact, we talked about systems of any order, but we particularly concentrated on second order systems. They needn't have constant coefficients, but they had to be linear. We were only studying linear equations. The first important thing, the first important property of linear systems, if they're homogeneous, no forcing on the right-hand side, so d2 y by dt squared plus p of t dy by dt plus q of t y equals 0, the first and lovely property is that if you have two solutions. You can take any linear combination of those two solutions, and that will also be a solution. And that's how we build the general solution of these equations. We find if the equation is of order n, we have to find n solutions of the equation, of the homogeneous equation, and then all we have to do is add one particular solution, and that gives us the general solution. Now we can't use any old n solutions of the homogeneous equation. We have to use essentially different solutions, and essentially different means linearly independent, or the solutions must have the property that their Wronskian is non-zero. Those notions are equivalent when we're talking about solutions of equations where the coefficients are continuous in the time interval in which we're studying the problem. When we come to the point of doing equations with constant coefficients, things get even easier. Because if we've constant coefficients, d2y by dt squared plus p dy by dt plus q times y is 0, we can generate solutions by letting y equals e to the rt. And then r satisfies a polynomial equation. If the equation is second order, it'll be just a quadratic equation. And then there are certain, if you have two real roots, then the solutions are a to the r1t plus b to the r2t. If they're repeated roots, it's e to the rt and t to the rt. If the roots are complex conjugate pairs, like a plus ib and a minus ib, then the corresponding real solutions are e to the at cos bt and e to the at sine bt. Okay, so that's pretty straightforward. Now, if we want to solve, so now we can get the general solution of homogeneous equations. By the way, even if the coefficients are not constants, we have the method of reduction of order to apply should we have one solution of a second order equation. By using this method of reduction of order, we can essentially reduce finding the second linearly independent solution to a first order equation. Okay, now for the inhomogeneous equations, we had two methods. Method of undetermined coefficients, which works in those cases where the coefficients of the homogeneous part of the equation are constants, and the right-hand side function is a combination of functions in the form t to the m, where m is 0 or a positive integer, times e to the at and cos or sine bt. Then we use the method of undetermined coefficients. If we can't use the method of undetermined coefficients, and we have two linearly independent solutions of the homogeneous equation, then we can use the method of variation of parameters to find the particular solution, in fact, to find the general solution. And that's a bit messier in terms of it's got more steps in it, but it is much more powerful in the sense that you will always be able to find the solution by following that route. The applications which are so important are to mass spring systems, oscillators, because you can sort of think of springs as being good paradigms for studying many, many features in all of the sciences. Then we have circuits. And again, for the circuits, you need to know Kirchhoff's laws in order to write down the differential equations for charge and current and things like that. Finally, we studied the pendulum. We studied the pendulum in part 2 of the course, imagining that we have very small oscillations around its stable equilibrium, the one hanging dead straight down. Okay, then in fact the equation was just like that for mass springs, just like the same for LRC circuits, and it was very straightforward to solve. In particular, we want to often understand when a circuit or when some mechanical system responds most strongly to some external periodic forcing. And so we learned about the phenomenon of resonance, that if you can force an oscillator with its natural undamped frequency, then the response is very strong indeed. And in fact, that's the way, as I've told you, radios and receivers work. The final part of the course, and what we're going to spend a little bit of time on today in the context of this particular example, is where you have a second-order system of two first-order autonomous equations. dx by dt and dy by dt are given as functions of the x and y, but the autonomous means that t does not appear explicitly in the equation. Now, the example, we've done several examples of the pendulum. We did the mixing problem where we had mixing in two tanks. We did the problem of a puck sliding on an icy surface with this sort of shape. And this is the one we're going to study today in great detail. And we also talked about rabbits and foxes. And in the rabbit-fox example, I gave out a handout, and all the conclusions are correct, but as Joel Fontes pointed out, I made an arithmetic error in calculating some of these coefficients. So this pile is the corrected first page of the stuff that I handed out last day, and you can collect this at the end of the lecture, or it'll be up on D2L corrected later today. Okay, so Joel, thank you for catching that. But the conclusions are the very same as far as the nature of the stability of all the equilibrium points. So now let's look at this particular example. To remind you, in this example, x is not actually that distance there, the horizontal distance. It's actually the distance along the curve, this potential. And y is the velocity along that curve. Okay, but given that, then the equations have this form. Gravity has been just made equal to 1, just for convenience here, or scaled out of the problem. So the question is, what are the various motions possible? Well, you can sort of look at the thing and you can sort of see a couple of interesting facts. Number one, you can sort of imagine that if you start here, right at the bottom, and stay there, I mean, that's where you'll stay. I mean, that's if you start at that point, you will actually stay at that point forever. Okay, so this is one equilibrium point, and this is another. Now, clearly, they are very different in nature. How one finds those points, incidentally, is one looks for the x, y values which make both f and g 0. In this case, those x, y values are x equals 0, y equals 0. That's this point here. And x equals 1, y equals 0. That's this point here. Okay, so there's the 2 points the equilibrium points. So does everybody appreciate how to find the equilibrium points? You set the F0 and the G0, and you look for joint solutions or values of a pair, x and y, such that both f and g are 0. Now, the next obvious question is, well, what would happen if I perturb this equilibrium? If I give the puck a little shove in one direction or the other, imagine I take this up here and give it a little velocity up here, what will happen? Will it stay just oscillating in the bottom? Or if the friction is very strong, it might just go up here and just slowly come back here, like that. Or it might make just one circuit like this and then go back like that. In which case we give three definitions of the kinds of stability. The first kind of stability is Lyapunov stable. Namely, if I start near this pair, 1, 0, the position is 1, the velocity is 0, and I give the thing, I move it slightly away from the 1, and I give it a little velocity, the question is, will it always stay in this neighborhood? For all time. For all time. If it does, we say that equilibrium point is Lyapunov stable. If the point is not Lyapunov stable, then we say it's unstable. For instance, here. An arbitrary little push either side, if I start it here and give it a arbitrary but small velocity, it will generally not stay near this point. It'll go way down here or go away down this side. Now, there are two very interesting but impossible to reproduce conditions, but nevertheless very interesting possible behaviors. You could say, give it a little push to this point here, and then give it enough velocity in this direction, negative velocity, so that as time goes to infinity, this guy will just climb up and stop here. Now, you have to, of course, coordinate the amount of velocity you give it exactly with the position that you've perturbed by. That does not, the fact that there is such an orbit does not make the thing stable, because stable demands that you can give it any little push, any displacement, and any little velocity, and it should stay in the neighborhood of the top. But that clearly doesn't happen here. But nevertheless, in this xy, which we call phase space, the orbits that describe what happens here actually are very interesting. And we're going to learn about them today. We call them stable and unstable manifolds. Okay, I'll come and I'll write down the definition right now in a moment. Okay, so now the question is, what do we do? We have the equilibrium points. Our intuition, if we know that the thing is a puck sliding in this curve, our intuition also helps, and that's something we always appeal to. But the next thing really is we use our software, the JODE software. And the things I've handed out to you are this Andy Warhol looking like a big eye glob. This is the phase plane for this particular autonomous system, for this particular case, when I've picked the B, I called it E here, equal to 0.3. So there's a little damping. Okay, there's a little damping. Now, so what we do is we've established, we know what the equilibrium points are by calculation. So the next thing we always do is just go to the computer and play and see what things look like. Now, notice that the point 1, 0, okay, the 1, 0 now becomes a stable spiral. It would be a stable node. The difference between stable spiral and stable node is as following. The spiral means that when you perturb, give it a little kick, it'll just oscillate, and with decreasing oscillations just come right? Eventually it tends back to the point. By the way, we call that point then asymptotically stable. Okay, asymptotically stable. Now, if the friction, if I'd made this friction be 4 or something like that, big enough, then in fact the friction would be so much that it wouldn't get to oscillate at all. It would just come down directly here, or maybe just one pass by here and come back and hit this. And that's it. That's a stable node. So if the friction is strong enough, it's a stable node. If the friction is relatively weak, then usually you have this stable spiral. In this case, it's a spiral. You can see that if I start near the point 1, 0, I spiral into it as t goes to infinity, right? So that's a stable spiral. Now, we always remember that it's important, it's useful to know, in this xy plane, here's 1, 0, here is 0, 0. We know this spirals in like this. I would like to know, in this yx plane, what is the set of initial conditions that if I start at that, any member of that set of initial conditions, I will end up at this point. Now we give that set a name. It's called the basin of attraction. Okay? Now in the one-dimensional problems, do you remember when we did a problem like dx by dt was x times 1 minus x? In the one-dimensional problems, the equilibrium points now are 0 and 1. All we had to do is draw the graph of x times 1 minus x, which looks like this. And then because the graph, the right-hand side is positive here, dx by dt is positive, x increases as t increases. We know to put the arrow there. On this side, because the graph is negative, this is negative, so dx by dt is negative. So if we're out here, at an x out here, dx by dt is negative, x decreases as t increases. Likewise over here. So we can read off from this graph what's going to happen. This is asymptotically stable, and this guy is unstable. Okay? So in this case, we were able to easily identify what's the basin of attraction for this guy. Well, it's as long as you start greater than 0 and less than infinity, you will always end up at the point 1. But in the two-dimensional problems, that's not so easy to determine that basin of attraction. But this is where these wonderful things called stable and unstable manifolds come into play. When we study the neighborhood of the unstable point, actually this is the way up, the unstable point now is 0, 0. In other words, the thing is sitting at rest, so its velocity is 0, sitting at the position x equals 0. It turns out that that orbit that I described if you start at an initial condition, supposing you start over here, an initial condition with a certain x, and give it a certain negative velocity, so that means you're starting here on the thick line, x greater than 0 with a y slightly negative. If you give it just the right velocity, it'll, as t goes to infinity, it'll just crawl back up to the top and stay there. The unstable manifold, by the way, is that set of points for which if you run time backwards, if you start at the point and run time backwards, you go to this point. Now, the unstable manifold here, look at the guy coming out of from the 0, 0. It winds around and ends up in 1, 0. It ends up at the asymptotically stable point. But now look what the stable manifolds do. They bound the basin of attraction. What I did here was I knew the unstable manifold was roughly in this direction. I clicked the mouse just here, and I ran the program backwards in time. I ran it from t equals minus 30 to plus 30. So I got the forward in time motion from here and the backwards in time. And the backwards in time runs like this. Okay? And then if I start this side, that's this side of the guy here, the orbit that's given a positive velocity starting just to the left here, it'll just get to the top. This is this orbit here. This is this stable manifold. Now, we were able to actually write down equations for those in the case where the b was 0, because then the trajectories were defined by dy by dx is x minus x squared over y, which we could actually integrate. And we could look at the curve that went through x equal y equals 0. And if you remember, it looked something like this. So this was the this is the case when b was 0. We've got dy by dx is x minus x squared over y. Integrating that up, I get y squared over 2 minus x squared over 2 plus x cubed over 3 equals constant. Okay, so they were all the curves, and the particular curve that goes through 0, 0, of course, E is 0. If I put x equal y equals 0, it's E equals 0. So that's this curve, and this curve actually then looks like this. Here's 0, 0. It looked like kind of a half a figure of 8, just a loop like that. Okay, now, once I have the friction in there, I can't, of course, solve it exactly anymore, so I had to use the computer. But the computer then drew me out. If I started just to the left here, I got, as I went backwards in time, I get this. This is the stable manifold of the unstable point. And if I start this side, the stable manifold runs like this. And the starting points, all the points that are in here, in between those two manifolds, that's the basin of attraction for this asymptotically stable spiral point. So in other words, if you start anywhere outside here, if I start up here, I'll go whoop, 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 like that. Okay, I have to start in here, so that gives me the set of x positions and y, namely the initial velocities and the initial positions. If I start in this area between these two stable manifolds, I will end up here. Now that's very useful. It's very important to be able to calculate that sometimes. You would like to know, for instance, like in the rabbits foxes situation, you'd like to end up, say, at one of the equilibria, and you'd like to know how many foxes do I put into the environment and how many rabbits do I put in initially, so that I know I'll definitely end up there. Okay, and not end up going off somewhere I don't want to go off to. Okay, so let me now write down then the definition. The definition. So, I'll write it here. So the stable or unstable manifold of an unstable saddle point equilibrium XE, YE is the set of initial conditions it's the set of starting points such that the resulting orbit XTYT tends to XEYE as for the stable manifold as t goes to plus infinity and the unstable manifold as t goes to minus infinity. Now it's very interesting that these curves play such an important role. And you can't, generally you won't be able to calculate them, but it's not hard to use JODE. You just give a little click near the unstable point, let time run backwards, and that'll draw you the stable manifold. Now I believe GHW number 12 is asking you to do these things. How many of you have actually run the program backwards and found the stable manifold? Yeah, and did you found it? Draws out these things? So it's pretty miraculous that these guys are very useful, even though they're connected with unstable points. And you think, what the heck is, why are we interested in unstable points? Because the thing is never going to stay there. But there's certain features about these unstable points which allow us say something about the whole picture, the whole geometry of the phase plane in general. So, first thing we do, we work out what the equilibrium points are. If possible, we also try to understand what the physics of the situation, what's the science, what does this represent, so that we have some intuitive recourse. In other words, we ask, is this a sensible answer to the question? I mean, when we come up with some solution, either from JODE or from our analysis. Then the next thing is we go to JODE and we play. This is how science has changed dramatically in the last 50 years. It used to be we had theory and experiment. An experiment meant rustling around in your laboratory with all sorts of pipettes or electrical equipment or whatever, or weighing and balances, and doing real experiments and measuring. And then you would compare measurements with some outcome from a theory, which was usually some analytical solution in some very special case. But now, with the advent of high-speed computers, we have simulation. Computer simulation as the third leg of investigative science. And it's absolutely central now, because it's much quicker. If you believe in your model and you write the proper algorithm to reflect that model, the computer acts much more quickly than you do experiments. I mean, I remember one of the first jobs, it was a very revealing job, you know, coming from background of theory and in physics and in mathematics. You tend to think, you know, you tend to go along to your experimentalist friends and say, hey, why don't you try this? You know, you say, change this parameter, or just try this, and maybe you'll see this. But it takes him weeks to sometimes to get the conditions. I mean, he's working, say, with fluid in some rotating jar, and you might need a fluid with a totally different Prandtl number. You'd have to chase off and find a fluid with this right Prandtl number. Like, Prandtl number is the ratio of viscosity to thermal conductivity. So it's not easy to respond quickly with experiments. But with computer experiments, it is. You can change parameters very quickly and then explore. So the great thing that you guys have, you know, there's a lovely story about the theoretician. The farmer comes to this professor in the university and he says, "Professor, I hear you're an expert on diseases in cows." "Yes, I am, says the fellow. So the farmer says, "My cow is very sick." "Oh, indeed, he looks very sick indeed." And he says, "But look, I have a solution. But try this, give him this pill." So farmer comes back a week later. "How's the cow?" "Cow's even sicker, can barely stand up." "Don't worry," says the professor, "I have another solution." Okay? So the farmer takes the second solution and gives the thing to the cow and comes back a week later, but there's no cow. "And how's the cow?" "Cow is dead." "Oh, what a pity," says the professor, "and I had so many other good solutions." So that's like kind of the theoretician talking to the experimentalist. You know, it's why don't you try this? It takes months, but the great thing about the use of simulation is you can do all this relatively quickly. But you have to have good algorithms. You have to know that your numerics is producing what your differential equations say, rather than producing something all on their own, which is irrelevant. That's where your intuition comes into play. So the second thing you do after establishing the equilibrium points and trying to get an intuitive feel for what should happen is you play, you explore using JODE. Now, it could happen that you don't have a computer handy, but you really need the answer. You know, your boss comes to you and says, "Fred, I need the answer." "Oh, sorry, sir, the computer system is down." "And will tomorrow be soon enough?" "No," says the boss, "I need it now." It reminds me of that's another story, but it's no, there was one very, very famous kind of in Princeton. This guy was doing his qualifying PhD exam, and the professor says, "What's Stirling's formula?" Stirling's formula tells you it's an approximation for factorial n, for n large, in terms of exponential, and so it says essentially that fac n looks like e to the n over whatever it is. And the guy says, he kind of dismissed the professor. He says, "Look," he says, that's just calculation." He says, "Whenever I need to have Stirling's formula, I can find it, I can look it up." And the professor says, "You need it now, boy." So professors are like that. Anyway, where was I? So the simulation is this great tool. But if the simulation isn't available to you, and you need the answer now, your boss has come to you, "Fred, I need the answer. I want to know roughly what's going on in this system. Here." How do you do it? Well, this is the step which we call local analysis. So now I'm going to show you what we do with local analysis. Local analysis near the equilibrium point. XE, YE. So, you simply set X equal XE plus capital X. Y is YE plus capital Y. You substitute that into the equations, and you neglect all terms which aren't linear in cap X, cap Y. So let's do it for our 0, 0 point here. Let's take the example of XE, YE being 0, 0. So then I get X is going to be just big X, so I get d big X by dt. And on the right-hand side, I just get Y. dy by dt will be d big Y by dt minus b times 0 plus big Y, which is minus b big Y, plus 0 plus x, which is just x, just x, and then minus x squared. That's it. And the only thing here, now, this is just, so what you would find in general, that df by dx at 0, 0 is 0. df by dy at 0, 0 is 1. dg by dx at 0, 0 is 1 minus 2x. dg by dy at 0, 0 is minus b. So that's A, B, C, D. Now, at x equals 0, this is just 1. And that's what we find. You see, the C, we neglect the x squared. The C is 1. The D is minus b. The A is 0, and the B is 1. So now we've these two equations for big X and big Y. Well, eliminate the y from here, put it in here, I get d2x by dt squared, plus b times y, which is b times dx by dt, minus x equals 0. Solutions. X is equal to e to the rt, and the r is two roots, r plus and minus is minus b over 2, plus or minus the square root of 1 plus b squared over 4. One root is positive, one root is negative. That's why I call them r plus and r minus. So what's the solution? The solution is capital X, which is x minus 0, is equal to a e to the r plus t, plus b e to the r minus t. Right? It's just the solution of this equation. And what's the y? The y we compute, it's just dx by dt, and that's the same as y minus 0. That's the derivative of this. So it's r plus times a e to the r plus t, plus r minus b e to the r minus t. Remember, r plus is positive, r minus is negative. Now I'll write this in a slightly different way. I have x minus 0 is equal to, and y minus 0, this sort of vector, is ae to the r plus t times 1 r plus be to the r minus t times 1 r minus. Okay? Now, the A and the B come from knowing x naught and y naught. Now, let's go over here. So, the set of initial conditions x naught and y naught, which lead to a solution where this x returns to 0, y returns to 0 as t goes to plus infinity, what has to happen here? This is positive. So as t goes to plus infinity, what does this do? So, yes, so the A has to be 0. So the stable manifold, by the way, let's work out A and B in terms of x naught and y naught. At 0, x of 0 is A plus B. Y of 0 is R plus A plus R minus B. Okay, so now let's work out what A is. To get A, I'll multiply the first equation by R minus and subtract. Okay, so I get y naught, okay, y naught minus R minus x naught. That's equal to A times R plus minus R minus. And to get B, I'll do the same with the plus. Minus R plus of x naught is B times R minus minus R plus now. Okay? So now you have A and B. Now you have A and B. So, the stable manifold is given by A has to be 0. Right? Because then x minus 0 and y minus 0 tends to 0, 0, as t goes to plus infinity. Okay? So in this case, what is the stable manifold? Well, the stable manifold is A has to be 0, so y of 0 has to be minus R minus, or sorry, plus R minus times x of 0. Now this is just minus p over 2, sorry, minus b over 2, minus, did I write p over here? No, b, yeah. 1 plus b squared over 4 times x of 0. And that's approximately, for b small, this is equal to minus x of 0. Because for b small, this is the biggest term here. Now, this is really, it's not really so much the stable manifold, it's the tangent. It's the tangent to the unstable manifold at x e equals 0, y e equals 0. So it tells you the tangent to this curve. Where are we? Here. So it says this curve, the tangent here is y is minus x times b over 2 plus the square root of 1 plus b squared over 4, which in our case is the square root of 0.3 over 2. So it's 0.1. It's roughly minus 1.15x. So that's the line y equals minus 1.15x. That's the tangent. This is a curve. This isn't a straight line, but locally, the tangent to it, locally it looks like a straight line going through the 0, 0. So now you can tell your boss, well, I can calculate a little bit more of the picture. I can calculate a bit more of the picture. I can tell you that this is unstable, this is stable. Okay, and you look in the neighborhood here, and the stable manifold will look like this, and the unstable manifold will occur when b is 0. Because when b is 0, then this is gone. So now if I run time backwards, this goes to 0 as time goes to minus infinity. And this is y of 0 is equal to r plus x of 0. And this is equal to minus b over 2 plus the square root of 1 plus b squared over 4 times x of 0. So this is the set of points. Y is plus, roughly plus 1x. Or if we take off, it's 0.85x. So this slope here, the manifold that takes off from the origin and winds its way in here to the stable fixed point, stable spiral, is in that direction. So you see, you can now tell your boss about, things like this. Now you can say, well, let's do the same for the other fixed point. Let's go through the very same analysis around the fixed point 1, 0. Okay? Any questions, by the way, on the first bit? Now I'm not yes?
Under the radical up there, where it's b squared over 4,
yeah.
Is that the friction b, or is that...
That's the friction b. It's in I think I called it E in the notes. It's 0.3 in the picture.
And that's different from partial f over partial y?
Yes, it is. That's why I used E. Yes, absolutely correct. It's not this guy. Yep. Right? Okay. So now we have this. Now, supposing we try and work around the point 1, 0. Well, now the difference will be just here. And let me put E here now, because Stephanie's point is very good. That's E here. Okay? Now it's E times y plus 1 plus big X minus 1 plus big X squared. Okay? Now, when I calculate this out, this is the 1 plus x minus 1 minus 2x minus x squared. The 1's cancel, as they should, and so I get minus x on the right-hand side because we neglect the x squared. So the difference is this becomes a plus. Now let me use E here. Now, what are the roots? Well, it depends whether E squared is greater than or less than 4. But let's imagine E is small. Can you wait a minute, fellows? R plus or minus is now minus E over 2 plus or minus I times the square root of 1 minus E squared over 4. So now what are the solutions? Now the solution is A, e to the minus E over 2t cosine the square root of 1 minus e squared over 4t plus b e to the minus e over 2t sine of square root of 1 minus e squared over 4t. And the y then is just the dx by dt, whatever you get. Now, what's that trajectory? That trajectory is it just spirals in. So you know near here, if you start near here, you spiral into this guy. So by doing the local analysis, you can tell what is the behavior of the solutions near these equilibrium points. Now that's all formalized in a graph that I give you in terms of A, B, C, D, where A is this guy, B is this, C is this, and D is this. And if this should come up in the final, I'm going to give you all that information about how to compute, do local analysis near the fixed point. So I won't expect you to remember everything. Now that's all you can do, except you can also ask the guy, the JOD program, to give you slopes. It can give you the direction fields. So it gives you these little arrows. Okay? But like I say, if you don't have the computer, at least you have this much. And from this much information, since these are really the two most interesting points in the phase plane, you can more or less sketch out what the rest of the phase plane is going to do. What's actually going to happen, as we know here, we'll get this guy will go off something like this. This guy will come around like this. So this will be the basin of attraction of this point, and then everything out here does this. So the various orbits you can have then are the following. Any point in the phase plane will end up doing this, this, or this. This guy here is the point that starts up here. He comes, that's him. This guy here starts up here, goes up, doesn't quite make it to the top, and comes back like that. Actually, some of the guys, if you start here and go fast enough, you can go up like this and then come back like that. That's one of these orbits too. And then for a certain set of initial conditions, either starting here or here, you have enough friction that you'll just end up oscillating in here and ending up at that point. So this is the then extra tool you have to analyzing solutions of equations like this. The most important tool, though, is JODE. But with a little analysis, you can get part of the way. Very good. Are there any questions? Yes?
Yeah, I'm kind of curious. So if you were to try using the local analysis method when you have, say, fractional or negative powers of one of the variables, how would that work? What terms would you neglect that?
We're assuming that this guy is analytic near the equilibrium points, that you can write a Taylor series. Okay? So, we're not going to allow 1 over x to be f, or things. X. Again, that would make it non-analytic, so the derivatives mightn't exist at the equilibrium points. So then, yeah. So really, when you say, I'm asking that a Taylor series expansion works here, you're saying that essentially the partial derivatives have to exist as finite numbers. All right, you've been a great class. We'll see you.